How do we balance a reaction? How many zincs? So how many zincs are on the reactant side? How many zincs on the product side? So zinc balanced. Yep. How many hydrogens? And? 2. Is it balanced? No, what do you have to do? We add 2 in front of the H+. Are zincs balanced? Hydrogens? Zinc? Hydrogen? Hydrogen? Okay, yeah, everything's nice and balanced. We're happy. We can move on. Okay. In this case, we did do a redox reaction. Zinc starts at what oxidation state? Neutral, so 0, and it goes to +2. So what happened to zinc? It lost electrons, so it was oxidized. What happened to the hydrogen? It went from +1 to 0. What happened to the number? The number got smaller. It was reduced. Okay, so we did do a redox reaction in this case. And as far as balancing goes, we're like, hey, that's no big difference from what we've seen before. But other times, it may not be as trivial. So if we take a look at this reaction, and we go through to try to balance this out, how many tins do we have on the reactant side? Tins on the product, iron on the reactant, iron on the product. 1. So we look at that and say, oh, according to all our rules, that's balanced. Turns out it's not balanced. Okay, the reason it's not balanced is if we now take it a step further and we look at the charge. What is the overall charge on the reactant side? It is a +5, and on the product side we have +6. Our charge is not balanced, which means we did not balance our electrons. So somehow in the course of this reaction, electrons have disappeared. Yes, that can't physically happen. Okay, so this equation is not balanced. What if we went back and checked that one that I said was so trivial? Remember, the only thing we changed is we put a 2 in front of that H+. What is the overall charge on the reactant side? Is it +1? Why is it +2? There are 2 H+. So there's a +2 on the reactant side. On the product side, what's the charge? +2. So when we balanced it the standard way, we still balanced the charge. We just didn't have to do it explicitly. Okay. When we move to the next equation, it doesn't quite work for us. If we run our standard method, it doesn't work. It's not balancing out the charge appropriately. Something is wrong. Okay. There are a variety of ways to go through and adjust and account for this. What we're going to walk through is look at one way to go through and approach this. Your textbook gives you a slightly different way. I will caution you that the textbook, in the process of giving you a different way to do it, also gives you stupidly hard problems that follow no real logic as far as balancing. Right? So if you asked a tutor or even me to go through and do it, I could do it, but I would have no way of telling you how or why I did it. Okay? I just kind of figure it out and it comes up with it. So there are a couple ways we could approach this by just trying to balance out the charge and by changing things randomly until we balance it out. If you're good at the random changing, that's cool. I can accept that. Okay, but what we're going to do instead is take advantage of redox reactions. So what we're going to do is split this equation into 2 parts, where one part is the reduction and the other part is the oxidation. So all we're trying to do is come up with some way to separate that information away from each other. Okay? Because I know they have to happen with each other for the overall, okay? But I can pull out the reduction and just look to see what happened for the reduction. Okay? And I can look at just what happened for the oxidation. So to do this, I need to take a look at my reactants. And I want to see what it changed to, or what it was most likely converted to in the products. So tin S plus 2, what the heck? Sn plus 2, or tin plus 2, was most likely converted to what in the products? Tin plus 4. The most simple or the most comparable thing that converted across. So I will write a new equation where I'm now looking at just tin plus 2 going to tin plus 4. And I will also write an equation where I'm looking at iron plus 3 going to iron plus 2. Okay. So the idea is to kind of slowly stepwise through our information and tease out of it the information about electrons. Why do we need electrons? Because the charge didn't balance. We balance our charge by looking at electrons. What happened to tin plus 2 to go to tin plus 4? It lost 2 electrons. So I need to include that now in my equation. Where do I put those electrons? Okay. Let's say you don't know. How many of you know? Okay, so I see 2 hands. The rest of you don't know. So guess what we do? Yes. I'm going to put an electron on that side. What's the charge on the reactant? It's a +1. Why +1? A +2 and a minus is +1. Charge on the product? +4. Did I get closer to balancing the charge or further? Further. That means I did something wrong. So where should I put the electron? On the other side of the equation. Whoa, okay. So let's go ahead and erase that. And I'll put my electron on the other side. What's the charge on the reactant? Charge on the product? +3. Did I get closer or further from balancing the charge? Closer. Am I there yet? What do I need to do to balance the charge? I need another electron. So I could write plus another electron. Or I'm adding 2 electrons. What's the charge on the reactant side now? Still +2. What's the charge on the product side? +2. Are my charges balanced? Yes. Now I'm happy. All right. Now what I've done by doing that is balanced the half reaction. Because it's only half of the overall result. That's why it's our half reaction. There are some problems with this. Electrons, tiny, nasty, vicious little animals, or parasites. They cannot, whoa, excuse me guys, sorry. Okay. They cannot exist on their own. What does this equation show is happening? That they are on their own. Okay. So this is why it's a half reaction. This reaction cannot happen on its own. Another reaction must match it to make sure those electrons get shifted to a new host organism.
Those 2 electrons of tin or 2 electrons of randomness?
Those 2 electrons came from the tin. So for tin to go from a +2 to a +4, it had to do what? Lose 2 electrons. So the 2 electrons we're showing in the product are the 2 electrons that came from tin +2, so that it could now become tin +4.
You don't just leave it 2e minus.
For the half reaction, I do. Okay. And what we just said is that the electrons are parasites that cannot exist on their own. They need a new host. Okay. That other host is going to be the other half of the reaction. So before we do that, what type of reaction occurred to tin? It was oxidized. How do we know that? It lost electrons. Electrons are a product. We have an oxidation reaction, which means what had better happen in our other reaction? We better have the reduction. So let's take a look at that one. Okay, we have Fe plus 3 going to Fe plus 2. What happened to the iron?
Gained electron.
It had to gain an electron. Well, if I don't know what gain an electron means on what side of the equation it is, what should I do? Guess. What's the charge on the reactant side? What's the charge on the product side? Did I get closer or further to balancing the charge? Further. What does that mean? I put the electron in the wrong spot. What's the charge on the reactant side? What's the charge on the product side? +2. What I now have is my balanced half reaction for iron plus 3. The electron was on the reactant side, which means iron plus 3 had to accept an electron, which means the reaction that occurred was reduction. And go figure, I actually color-coded it, which was pure luck, by the way. Right? So now what do we do with this information that we've split these into our half reactions and we make sure our half reactions are individually balanced? Exactly right. We'll smush them together. Okay? So on the reactant side of the equation, what do I have? I have tin plus 2. What else do I have? Iron plus 3. What else do I have? Plus an electron. On the product side, what do I have? Tin plus 4. Well, that's a 4. Plus? You had to switch the color on me. Thanks for that. Plus 2 electrons. Okay. If I begin and end with the same thing, what does that mean? Nothing happened to it. So what can I do to simplify this equation? I can erase 1 electron from the reactant side because I can cancel it with the 1 electron on the product side, and I end up with this equation. Just canceling like terms across the equation. Okay? So far, so good. All we've done is added these two equations together. We now have an equation that if we look at the charge, what happens? Charge on the reactant side is plus 5. Charge on the product side, also plus 5. Hey, it's balanced. So now we can go home. What did we say was the issue with electrons? They cannot be by themselves. Vicious little parasites. What's going on with this electron right now? It's hanging out by itself, which means I did not set up this equation properly. Just because the charge is balanced doesn't mean it's perfect. If I have an extra electron hanging out, that reaction doesn't work. So what I have to go through and do is now backtrack to my original equations and say, okay, what do I need to change about these equations that when I add them up, the electrons cancel? What's that? I can accept that. What happens if I convert another iron to iron plus 2? What do I need? Is that equation balanced? Fe plus 3 to Fe plus 2? No. How do I balance it? I need another electron. Now what happens when I add these two equations together? What's the reactant?
2Fe plus 3.
Man, you guys had to keep doing the color coding switching on me. 2Fe plus 3, what else?
Plus
Okay, 2 electrons. What else is a reactant? What else is on the reactant side? Where are the reactants on our arrows? Plus tin plus 2 goes to form what are our products?
2Fe plus 2.
I have 2 Fe plus 2s. What else? I have an Sn plus 4. What else? Plus 2 electrons. Now that I've got my two equations, what can I do? Anything cancel out across the reaction? Yeah, my electrons do. Charge on the reactant side. Plus 8. Charge on the product side. Plus 8. Does the charge balance? Yes. What's the question?
Why 8 isn't?
Okay, I was waiting for someone to ask that. So we have Fe plus 3 plus our tin plus 2, right? So the tin is a plus 2, the Fe plus 3 is a plus 3. How many tins are there? Or sorry, irons. How many irons are there? There's 2 irons. So I have another plus 3. Plus 3 plus 3 plus 2. That is 8, right? Do you just not like it? Do you see where I'm getting it?
No.
Is it not showing up?
It's showing up.
did we do all that work though beforehand? If we could have just done this then, which is like.
How did you know you needed 2 irons?
Just did.
There's the problem.
Well, I mean.
Okay. So you can go through and by inspection, if you're lucky, you can look at your equation and predict how much you need of each to make sure your charges balance out. Okay. The problem is sometimes it's not obvious. You need some way to organize it where you can set up this method. The half reaction method does that for you.
After the half reaction,
We'll come
you
back.
have part that we have this row of electron, and then you added it to the iron. How would I know who has that?
What was stated is that we should add more iron. Okay, so we added Fe plus 3. Okay, because I don't want to add a new iron, I have to add the exact same iron that's already there. Fe plus 3 to Fe plus 2. Is that half reaction balanced? So what do I need to do? I need to balance that half reaction. How do I balance Fe plus 3 to Fe plus 2? I need another electron. Okay. Now what happens? Now I add them up and I can see my electrons cancel out, which is a separate question from your charge. So then, are you okay with the charge now? Yeah,
I'll come back to it.
if we need to, okay.
So because you had to add an electron on the reactant side when you're fixing the iron,
Mm-hmm.
you do like 2 Fe plus 3. That's why you
Yep.
added 2 there.
So if I write 1 and 1 and 1 and 1 and put a plus symbol here, what does that equal? 4. Is that any different from saying 1 plus 1 plus 1 plus 1? How many 1s do I need? It's the exact same mathematics symbol. All we're doing is just adding down that column. Anything on the reactant side gets added up and totaled as our end result. Anything on the product side gets added up and totaled as our product.
So on the tin side, since we
On the-
added 2 electrons, you add 2.
So we have to make sure that our electrons balance out. So when we add all of our equations up, our overall equation has no electrons in it.
Right.
And to do that, what we noticed is that we had an excess of electrons on the product side, okay, before we added that second tin. So how do I get rid of that excess of electrons on the product? What do I need to see on the reactant side? I need more electrons. So what I will do is run the reaction that consumes electrons again. What if I had 3 extra electrons? I need to keep running the reaction that consumes those electrons to balance it out. Okay. The only reason we split this into 2 equations for the iron is just because that's what was actually said by you guys. Okay. The other option is we look at, well, actually before we do that. Okay, so does that kind of get at what you're asking?
I don't know.
I don't know. Okay, let's.
Adding another iron doesn't change what it is with the product.
No. So adding the other iron, as long as we account for it on both the reactant side and the product side, it stays balanced. The iron is still being balanced out. All that we're doing is accounting for that extra electron. Because electrons are parasites and cannot exist on their own. They must balance out in your equation.
But why do we pick iron instead of tin?
What happens if we'd added tin?
You'd have more electrons than you need.
If we did tin plus 2 to tin plus 4, how many electrons would we have on our product side now? We'd have 4 electrons on the product side versus 1 electron on the reactant. Did we get closer or further from balancing out the electrons? We got further. So doubling tin was a bad option. Does that make sense?
Complexity is good, okay.
Not any more complex than this, thankfully. Yeah. This is where I highly recommend and caution you on using your textbook within the balancing reactions. The reactions that they give you in the textbook for balancing redox are stupidly hard. Okay? They give you some other method, which this kind of goes back to the crossover thing, and they ask you to apply that to, like, they give you an example It's really straightforward. And you're like, oh yeah, I get it. The next example they give you is 50 times the difficulty where the crossover method thing that they show you doesn't work. Yeah, it's awesome. Okay, so the balancing on oxidation reduction reactions, horrible in the textbook. I do not recommend it.
Yeah, I think I'm gonna articulate my question now.
Yes?
So, trying to figure out the 2 for the iron, that seems like that's adding more than we need by 1. Because if we only have, trying to balance, we've got 3, well, when you had 1 electron plus the Fe plus 3, they gave us 2, plus 2, it evened out. Why do we have 2 Fe?
So remember what we've got here now, and this is where this line may be coming into a problem as well, is we had initially added just these first 2 equations, saw it didn't work. Okay, so the next suggestion was we need to balance out the electron on the product. So that means I need to add another equation in here with electrons on the reactant. So we wrote a new equation with electrons as a reactant. Right? We then added all of our equations up. How many ions are on the reactant side? 2. 1, 2. How many electrons are on the reactant side? 2 electrons, right? Sorry, just because you got it doesn't mean I can't stop. How many tins on the reactant side? Just 1 tin. We now move to the product. How many irons do we have on the product side? 2 irons. How many tins do we have on the reactant side? How many electrons? 2. Now what we can go through and do is say, do we have something that shows up the same on both sides? Yeah, what is that thing that shows up the same on both sides? The electrons. So what can we do? We can cancel them out. So those won't show up in my overall equation. All that shows up is the correctly balanced now irons with tins. How many irons in the reactant side?
2.
How many irons in the product side? How many tins in the reactant side? How many tins in the product? 1. Still balances out the same way as we've done before. The one extra step we need to verify is what happened to our charge. What is the charge on the reactant side?
8.
Tin brings in a +2 charge. Iron brings in a +3. There are 2 irons. So what does that mean?
6.
I need another +3, which gives me a +6 plus the 2 from tin. Charge a +8. What happens on the product side? 2 irons, but what's the charge on each of the irons?
2.
+2. So what's the charge contribution from iron +2? +4. Charge contribution from tin. What is 4 and 4? 8. Do my charges balance? Yes. Atoms balanced, charges balanced, equations balanced. Yippee, move on. Hi? Question?
You knew to add like the second E-magnetized iron because the electron was by itself when you checked it.
Perfect. Exactly right. We knew to add that extra equation because the electrons ended up showing up in our overall equation. And electrons cannot show up there. Sorry.
So when there's an extra electron, you just add the entire equation again.
You have to add the entire equation again. Okay, we can't just add an extra electron in there because then where did that electron come from? We just invented it. We can't invent it. It has to come from or be consumed by something. Hi? Y'all happy with that? Happy enough.
Wait, so, because, sorry,
No, you don't apologize.
because the +2 electrons on that side, that's why you added another equation. Because you have to have 2 electrons on both sides.
Let's go back to our check again.
Well, is that why?
Ish. And actually, before we just do the check, we can do this without all my handwriting because I've got it typed. So we've got our 2 half reactions, right? Within these half reactions, are each of the half reactions balanced?
No, they are not.
They are not balanced because our charge does not balance. So what we have to do is account for that charge balancing by adding electrons in. All right? So we added 2 electrons for our tin to balance out the tin. For our iron, we have to add 1 electron. Then what we do is just add our 2 equations up. If these are half reactions, if I take 2, what's half of 2? 1. So if I take both halves of that, 1 and 1, what should I get?
2.
The overall thing, right? That's what we're doing here. We're splitting it into the half reactions. When I add those two pieces back up, I'd better get the whole thing. Okay? So now when I go through and add those two equations, directly as written, what do I notice? There's a free electron floating off on its own. That electron cannot exist on its own. Which means I have to go back to these equations and say, how do I manipulate what's up here to make sure no electrons come out of this, either as a product or as a reactant? Right, it's that whole parasite phenomenon. So I can now go back up to my equation and say, okay, I need an extra electron as a reactant. Which equation gave me electrons as a reactant? The iron one. Right? I need 2 electrons. So how can I get that 1 electron to become 2?
Put a 2 in front of it.
I multiply by 2, but I can't just change the number of electrons because then is that equation balanced? No, I have to balance the whole equation by 2. So if I multiply, let's see if I've got it here, the 1 electron by 2, I have to multiply the iron plus 3 by 2 and the Fe plus 2 by 2. So that I now go through and balance this out, the net result is my electrons show up as both a reactant, come on pen, a reactant and a product. Electrons do not show up in my overall equation, and I have now accounted for both the atoms and the charge. Okay? That is how you go through and approach that. Exciting stuff. Okay, on that note. Yes. Go ahead and do this. For those of you that think you can do this in your head, that's fine. Go ahead and do that. Just realize there is an easy way out for me to test, can you do it correctly? For that second question, for balancing that equation, what I will ask is how many electrons were transferred? All right, if you do not know the half reaction method, you will have a hard time figuring out how many electrons were transferred in that second equation.